There is something deeply uncomfortable about the way we talk about steel today. We are told, confidently, repeatedly, that modern steel is the pinnacle of human progress. Cleaner, stronger, more precise, engineered down to the molecule, computer-modeled, lab-tested, quality-controlled. Compared to that, ancient steel is supposed to be crude, romantic, perhaps, but ultimately inferior. And yet, history refuses to cooperate with that story. For nearly 1,000 years, a class of blades existed that modern metallurgy still struggles to fully explain. Swords that bent without breaking, edges that stayed sharp after battles that destroyed armor, blades that could slice through iron yet survive impacts that would shatter many modern steels. These weapons were not myths. They were not magic. They were Damascus steel. Here's the uncomfortable part. When modern scientists first examined surviving Damascus blades under microscopes, they expected to find imperfection. What they found instead looked disturbingly sophisticated: layered microstructures, carbon distribution patterns, and internal architectures that resembled techniques we claim to have invented only recently. So the real question isn't whether Damascus steel was impressive. The real question is, why does steel made centuries ago sometimes outperform steel made with modern technology? And more dangerously, what did we lose when we improved steel? That question is the crack in the foundation. Once you see it, you can't unsee it. Because if ancient metallurgists, without electricity, without microscopes, without chemical theory, could produce steel with properties we still admire today, then progress may not be a straight line. It may be a trade, and some trades come with hidden costs. Most people assume Damascus steel was simply folded steel, endlessly hammered into layers. That assumption is wrong and revealing. Folding alone does not explain its properties. Japanese swords are folded. Modern pattern-welded blades are folded. Yet neither truly replicates historical Damascus steel. The original material was something rarer, Wootz steel, produced in India and Central Asia. High-carbon steel melted in sealed crucibles, allowed to cool under specific, poorly understood conditions. Not optimized for speed, not optimized for mass production, optimized for structure. What mattered wasn't just the ingredients, it was the process. Slow cooling, impurities that modern metallurgy would classify as defects, trace elements like vanadium and molybdenum that weren't removed but integrated, carbides that aligned themselves into repeating patterns during forging. Modern steelmaking, by contrast, is obsessed with control. Remove impurities, standardize composition, eliminate variability, increase yield, reduce cost, increase scalability. Every one of those goals makes sense if your objective is uniformity. But Damascus steel wasn't uniform. It was adaptive. Its internal structure wasn't chemically pure. It was architecturally complex. The carbides formed bands. The ferrite matrix remained flexible. Hardness and toughness coexisted not by averaging out, but by separating roles within the same blade. That's the key idea modern steel often forgets. Strength does not have to mean sameness. In Damascus steel, hardness lived in the edge. Flexibility lived in the spine. Microscale heterogeneity created macroscale performance. Modern steel often pursues balance by homogenization. Ancient steel achieved balance through organized imbalance. This is where the myth of technological superiority starts to crack. Because modern steel is stronger by some metrics, tensile strength, yield strength, predictability. But combat blades, cutting tools, and impact-resistant edges don't live in spreadsheets. They live in chaotic environments where materials are stressed in multiple directions at once. Damascus steel was forged for chaos, and chaos punishes uniform materials. Here's where the investigation deepens. When modern researchers attempt to recreate Damascus steel, they often fail. Not because they lack skill, but because the system they work within is fundamentally different. Industrial metallurgy is designed to eliminate variation. Damascus steel depends on it. Ancient smiths didn't know phase diagrams, but they understood feedback. They watched color. They listened to sound. They adjusted forging based on feel. Knowledge wasn't written. It was embodied, transmitted through apprenticeship, not textbooks. When that chain broke, through war, trade collapse, colonial disruption, the knowledge vanished. Not because it was primitive, but because it wasn't documented in a form modern science respects. And so we labeled it lost. But perhaps abandoned is more accurate, because what replaced it was a system that values reproducibility over resilience. Steel that performs identically every time, until it fails identically. Damascus steel, by contrast, fails unpredictably, which is often another word for survives longer. This is the paradox no one likes to talk about. Optimization can reduce robustness. By removing impurities, we removed complexity. By chasing purity, we erased internal architecture. By standardizing steel, we made it easier to produce and easier to break under the wrong conditions. None of this means modern steel is bad. It means it is specialized, designed for bridges, buildings, cars, and machines that live in controlled environments. Damascus steel lived in hands, in motion, in impact, in life-or-death feedback loops. So when people ask, was Damascus steel better than modern steel? They're asking the wrong question. The real question is, better at what, and at what cost? Because once you understand that ancient steel wasn't inferior science but different priorities, the narrative flips. Damascus steel stops being a mystery of the past and becomes a mirror held up to the present. A reminder that progress isn't about knowing more. It's about choosing what not to discard. And that is where the story truly begins. Once you accept that Damascus steel wasn't an accident, the next question becomes unavoidable. If ancient smiths could create steel with such remarkable performance, why didn't that knowledge evolve into modern metallurgy? Why did we replace it instead of refining it? The answer isn't scientific, it's systemic. Modern steel is not designed by blacksmiths, it's designed by industries. After the Industrial Revolution, steel stopped being a craft and became infrastructure. Railways, skyscrapers, war machines. The requirements changed overnight. Steel now had to be cheap, scalable, predictable, and fast to produce. A blade forged over days or weeks by reading color and sound simply couldn't compete with blast furnaces pouring tons per hour. And here's the crucial shift. Steel stopped being optimized for performance in use and started being optimized for performance in production. Damascus steel failed that test. Its very strengths, sensitivity to cooling rate, dependence on trace elements, reliance on slow, controlled forging, made it unsuitable for industrial scaling. You couldn't guarantee identical results across thousands of batches. You couldn't automate intuition. You couldn't spreadsheet experience. So the system discarded it. But discarding knowledge doesn't mean disproving it. This is where modern misunderstandings begin. Many people believe modern steel is superior because it is stronger. But strength is a dangerously vague word. There are dozens of ways to measure it. Hardness, tensile strength, yield strength, fracture toughness, fatigue resistance, impact resistance. Modern steels excel at some of these metrics, especially those relevant to static loads and predictable stresses. Bridges don't need to flex unpredictably. Buildings shouldn't. Machines prefer consistency. Blades don't. A sword, knife, or tool lives in a world of sudden shocks, twisting forces, edge impacts, and microfractures. In that world, too much uniform hardness is a liability. It creates brittleness. When failure happens, it happens catastrophically. Damascus steel avoided this trap by being internally uneven, but deliberately so. Under magnification, historical Damascus blades reveal a landscape rather than a substance. Hard carbide bands snake through softer ferrite regions. Stress doesn't travel straight through the blade, it disperses. Cracks don't propagate cleanly, they get lost. Energy is absorbed, redirected, dissipated. Modern metallurgy knows this principle well. Today we call it composite design. The irony is painful. We now engineer layered materials, gradient steels, functionally graded alloys, and nanocomposites to recreate what Damascus steel did naturally. We simulate it in software. We manufacture it at enormous cost. Ancient smiths achieved it with fire, time, and restraint. So why wasn't this recognized earlier? Because modern science values explanation over outcome. For centuries, metallurgists couldn't explain Damascus steel using existing models. Its behavior didn't match simplified assumptions about purity and uniformity. Rather than expanding the model, the material was treated as an anomaly, or worse, romanticized into myth. Magic swords, lost secrets, legend. That framing was convenient. It allowed modern systems to dismiss uncomfortable evidence without confronting it. But as analytical tools improved, electron microscopes, spectroscopy, nanoscale imaging, the picture changed. Researchers began finding carbon nanotube-like structures, unexpected carbide alignment, self-organizing patterns formed during slow cooling. Not magic. Emergence. Complex behavior arising from simple rules given enough time. And there's the word modern industry hates most: time. Damascus steel took time. Cooling cycles couldn't be rushed. Forging required pauses. Heat treatments weren't optimized for throughput, but for transformation. In industrial terms, it was inefficient. But inefficiency is often just another name for redundancy. And redundancy is what makes systems resilient. Modern steel production removes redundancy wherever possible. It tightens tolerances. It eliminates variation. It assumes the environment will behave as expected. History suggests that assumption is optimistic. There's another layer to this story, one people rarely acknowledge. Damascus steel existed within a cultural ecosystem that respected material limits. Smiths didn't push steel to theoretical maximums. They worked within ranges they knew would survive misuse. Blades were expected to be abused, bent, resharpened, reheated. Modern design often assumes ideal usage. Failures are treated as misuse, not design flaws. This philosophical difference matters. Damascus steel wasn't designed to win laboratory tests. It was designed to forgive human error. That's why historical accounts describe blades bending and springing back, why edges dulled slowly rather than chipping, why these weapons survived generations. And that brings us to the most uncomfortable realization yet. Modern steel isn't worse because we forgot how to make Damascus steel. It's worse in certain roles because we intentionally chose different values. We chose scale over subtlety, efficiency over adaptability, control over complexity. Those choices built the modern world. They also erased entire categories of knowledge that didn't fit the factory. This isn't unique to steel. It's a pattern. Whenever a system optimizes for output, it sacrifices nuance. Whenever knowledge becomes embodied rather than documented, it becomes fragile. When the last master dies, the library burns with them. Damascus steel died not because it failed, but because it couldn't be industrialized without ceasing to be itself. And now, centuries later, we're circling back, trying to reintroduce heterogeneity, engineering imperfections, designing steels that behave less like spreadsheets and more like organisms. We call it advanced metallurgy. Our ancestors would have called it normal. So when someone claims modern steel has surpassed Damascus steel, the claim hides an assumption that the goal has always been the same. It hasn't. Damascus steel didn't lose a competition. It was disqualified for refusing to play by new rules. And once you see that, the comparison stops being about old versus new and becomes about what kind of future materials we actually want. Because the final irony is this: the more complex our world becomes, the more valuable Damascus-like thinking grows. And that sets the stage for the final question. If ancient steel was superior in ways we're only beginning to rediscover, what else have we prematurely left behind? By now, the conclusion should feel unavoidable, but still unsettling. Damascus steel was not surpassed because it was inferior. It was surpassed because the world it was built for disappeared. And this is where the comparison finally stops being about metallurgy and becomes about philosophy. Modern steel is engineered for certainty. It assumes that conditions can be predicted, loads can be calculated, environments can be controlled. When those assumptions hold, modern steel is extraordinary. Skyscrapers stand. Machines run for decades. Infrastructure scales beyond anything ancient civilizations could imagine. But Damascus steel was engineered for uncertainty. It lived in a world without safety margins defined by equations. A world where failure meant death. A world where materials had to tolerate misuse, bad angles, sudden shocks, imperfect maintenance, and human error. Its success wasn't measured by peak performance. It was measured by survival across unknown conditions. That distinction changes everything. Because when modern engineers attempt to recreate Damascus steel today, they often chase the wrong target. They replicate surface patterns. They copy layered appearances. They forge beautiful blades that look ancient, but behave modern. True historical Damascus steel wasn't defined by how it looked. It was defined by how it failed, or more accurately, how it refused to fail cleanly. When overloaded, it bent instead of snapping. When stressed repeatedly, it resisted crack propagation. When damaged, it degraded gracefully rather than catastrophically. These are properties modern materials science now explicitly tries to design into critical systems: aircraft components, medical implants, impact-resistant armor. We now call this damage tolerance. Ancient smiths called it good steel. And here lies the final irony. The future of advanced materials increasingly resembles the past. Modern research no longer seeks perfectly uniform alloys. It seeks gradients, hierarchies, multi-scale structures, materials that behave differently at different points under different stresses. We engineer internal architectures at the micron and nano level because we've learned a hard lesson. Homogeneity is fragile. Nature never builds uniform materials. Bone isn't uniform. Wood isn't. Shell isn't. They are layered, directional, imperfect, and astonishingly resilient. Damascus steel followed the same logic. It wasn't optimized. It was grown. Grown through slow cooling, through repeated thermal cycling, through patient forging that allowed microstructures to self-organize instead of being forced into compliance. It trusted emergence rather than domination. Modern metallurgy dominates materials. Ancient metallurgy collaborated with them. That difference explains why so much ancient knowledge vanishes when removed from its cultural context. You can't mass-produce intuition. You can't digitize judgment easily. You can't scale wisdom without flattening it. So the loss of Damascus steel wasn't a technical failure. It was an institutional one. When craft-based knowledge meets industrial logic, craft loses, not because it's wrong, but because it's incompatible. And that should concern us. Because the same logic now governs far more than steel. It governs food, medicine, architecture, education, even human relationships. Everything is optimized. Everything is standardized. Everything is made efficient. And everything becomes brittle in new ways. Damascus steel survives in museums and myths not because it belongs to the past, but because it doesn't belong to our systems. Yet. The deeper lesson of Damascus steel isn't ancient people were smarter. It's more uncomfortable than that. They asked different questions. Not, how do we maximize output? But, how do we ensure survival? Not, how do we eliminate variation? But which variations matter? Not, how do we control materials? But how do we listen to them? Until modern engineering fully relearns those questions, Damascus steel will continue to haunt metallurgy, not as a lost secret, but as a reminder. A reminder that progress isn't a ladder, it's a landscape. And sometimes the highest ground lies behind us, not because we couldn't go forward, but because we chose to walk a narrower path. Damascus steel didn't lose to modern steel. It was left behind by a world that forgot why it was made in the first place.